This scenario involves attempting to use a 408-208/120 transformer as a step-up transformer to convert 240 volts 3-phase power to 480 volts 3-phase power. The transformer was installed with the 240-volt side connected to what would normally be the low-voltage side, and the taps were adjusted to their lowest setting. This resulted in a voltage reading of approximately 490 volts on the primary side. The transformer exhibited several issues including sparking at the grounding lug, loud humming, and eventually, the ground wire burning out. No fuses tripped during this event. The fundamental issue lies in the improper application of the transformer. A 480-208/120 transformer is designed to step down voltage, not step it up in the manner attempted. The 208-volt secondary windings are not designed to handle a 240-volt input. Applying a higher voltage than the rated voltage to the secondary side can cause several problems. Firstly, overvoltage can lead to excessive current flow within the transformer windings. This can cause overheating of the windings and core, potentially damaging the insulation and leading to premature failure. Secondly, overvoltage can cause saturation of the transformer core. The magnetic core of a transformer is designed to operate within a specific range of magnetic flux density. When the voltage exceeds the design limits, the core can become saturated, leading to increased magnetizing current, increased losses, and audible humming. Thirdly, improper grounding can exacerbate the problems associated with overvoltage. The transformer case should always be properly grounded with a dedicated ground wire. A small amount of sparking at the ground lug indicates either improper grounding or ground fault within the transformer. A ground fault occurs when there is an unintended electrical connection between a live conductor and ground. This can cause a large current to flow through the grounding system, potentially damaging equipment and creating a safety hazard. The burning of the number 6 ground wire is a direct result of the excessive current and heat generated by the overvoltage and arcing. The ground wire is intended to provide a low impedance path for fault currents to return to the source, allowing overcurrent protection devices such as fuses or circuit breakers to trip and energize the circuit. However, if the fault current is too high or the ground wire is undersized, it can overheat and burn out. The loud humming observed is a result of the transformer core saturation. When the core is saturated, it can no longer efficiently transfer energy between the primary and secondary windings, leading to increased magnetizing current and audible noise. The fact that no fuses blew indicates that the overcurrent was not high enough to trip the fuses or that the fuses were not properly sized for the application. Fuses are designed to protect circuits from overcurrents, but they must be properly selected to provide adequate protection. A fuse that is too large will not trip quickly enough to prevent damage to the equipment. To correctly convert 240 volts 3-phase to 480 volts 3-phase, a dedicated 240 volt to 480 volt step-up transformer is required. This transformer is specifically designed for this purpose and will provide the correct voltage transformation ratio without the risk of overvoltage or other problems. To select the appropriate transformer, you need to consider the power requirements of the load. The load in this case is approximately 30 horsepower. To determine the required kilovolt amperes kVA rated of the transformer, you can use the following formula: horsepower times 0.746. The efficiency factor is approximately equal to the required kVA. In this case, 30 horsepower times 0.746 equals 22.4 kVA. It is generally recommended to choose a transformer with a kVA rating that is higher than the calculated value to provide some margin for future load growth and to ensure that the transformer is not overloaded. A 30 kVA or 50 kVA transformer would be suitable in this case. It is important to ensure that the transformer is rated for 240 volts primary and 480 volts secondary. The transformer should also be installed according to the manufacturer's instructions, including proper grounding and overcurrent protection. Proper grounding is essential for safety and to prevent electrical shock hazards. The transformer case should be connected to a dedicated ground wire that is sized according to the National Electrical Code (NEC). Overcurrent protection is also essential to protect the transformer and the connected equipment from damage due to overcurrents. Overcurrent protection can be provided by fuses or circuit breakers. The size of the overcurrent protection device should be selected according to the transformer's nameplate rating and the NEC requirements. It is also important to consider the inrush current of the transformer when selecting the overcurrent protection device. Inrush current is the high current that flows when the transformer is first energized. The overcurrent protection device should be able to withstand the inrush current without tripping. In summary, attempting to use a 480-208/120 transformer as a step-up transformer to convert 240 volts 3-phase to 480 volts 3-phase is not a proper application and can lead to several problems, including overvoltage, core saturation, improper grounding, and burnt ground wires. To correctly convert 240 volts 3-phase to 480 volts 3-phase, a dedicated 240 volt to 480 volt step-up transformer is required. The transformer should be sized according to the load requirements and installed according to the manufacturer's instructions, including proper grounding and overcurrent protection. Let's delve deeper into the NEC requirements for grounding and overcurrent protection. According to NEC Section 250.20, all electrical systems that are required to be grounded shall be connected to earth in a manner that establishes an effective ground fault current path. This path must be permanent and continuous and have sufficiently low impedance to facilitate the operation of the overcurrent devices in the circuits. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the ungrounded conductors. For example, if the ungrounded conductors are number 2/0 American Y gauge, AUG, copper, the grounding electrode conductor must be at least number 6 AWG copper. The equipment grounding conductor, which connects the transformer case to the grounding electrode conductor, must also be sized according to the NEC. NEC Section 250.122 provides the requirements for sizing equipment grounding conductors. For example, if the overcurrent protection device is rated at 100 amps, the equipment grounding conductor must be at least number 8 AWG copper. Overcurrent protection for transformers is covered in NEC Section 450.3. The primary overcurrent protection device must be sized according to the transformer's primary current rating. For transformers with a primary current rating of 9 amps or more, the overcurrent protection device must not exceed 125% of the primary current rating, unless the calculated value does not correspond to a standard size overcurrent device. In that case, the next higher standard size overcurrent device can be used. A secondary overcurrent protection device must be sized according to the transformer's secondary current rating. For transformers with a secondary current rating of 9 amps or more, the overcurrent protection device must not exceed 125% of the secondary current rating unless the calculated value does not correspond to a standard size overcurrent device. In that case, the next higher standard size overcurrent device can be used. In addition to the primary and secondary overcurrent protection devices, it is also important to provide overcurrent protection for the conductors that supply power to the transformer. The conductors must be protected by an overcurrent device that is sized according to the conductor's ampacity, as specified in NEC Table 310.15. It is also important to consider the ambient temperature when determining the ampacity of the conductors. If the ambient temperature is higher than 30 degrees Celsius, the conductor ampacity must be derated according to NEC Table 310.15. Let's also discuss the different types of transformers that are available. Transformers are generally classified into two main types: dry-type transformers and liquid-filled transformers. Dry-type transformers are cooled by natural air convection or forced air. They are typically used in indoor applications where there is no risk of fire or explosion. Liquid-filled transformers are cooled by a liquid, such as mineral oil or silicone oil. They are typically used in outdoor applications or in indoor applications where there is a risk of fire or explosion. In addition to the two main types of transformers, There are also several other types of transformers available, such as autotransformers, isolation transformers, and buck-boost transformers. Autotransformers are transformers that have a single winding that is used for both the primary and secondary circuits. They are typically used to step up or step down voltage by a small amount. Isolation transformers are transformers that have separate primary and secondary windings. They are typically used to isolate electrical equipment from the power supply, which can help to prevent electrical shock hazards and reduce noise. Buck-boost transformers are transformers that are used to adjust the voltage of a power supply. They are typically used to compensate for voltage drops or to provide a stable voltage to sensitive equipment. To reiterate, the correct approach involves selecting a dedicated 240 volt to 480 volt step-up transformer that is sized appropriately for the load. The transformer should be installed according to the manufacturer's instructions, including proper grounding and overcurrent protection. It is also important to consult the NEC for specific requirements regarding grounding, overcurrent protection, and conductor sizing. When selecting a transformer, consider the kVA rating required based on the horsepower of the motor. Use the formula horsepower times 0.746 equals kVA. Choose a transformer with a kVA rating higher than the calculated value to provide a safety margin. Ensure the transformer is specifically designed for stepping up 240 volts to 480 volts. Proper grounding is crucial. Connect the transformer case to a grounding electrode conductor, sizing the conductor according to NEC Table 250.66. Use an equipment grounding conductor to connect the transformer case to the grounding system. Size this conductor per NEC Section 250.122, based on the overcurrent protection device rating. Overcurrent protection is essential for both the primary and secondary sides of the transformer. Size the primary overcurrent protection device no more than 125% of the transformer's primary current rating, as outlined in NEC Section 450.3. Similarly, size the secondary overcurrent protection device no more than 125% of the transformer's secondary current rating. Protect the conductors supplying power to the transformer with overcurrent devices sized according to their ampacity following NEC Table 310.15. Account for ambient temperature when determining conductor ampacity, dirting as necessary per NEC Table 310.15. When dealing with electrical systems, it is always best to consult with a qualified electrician or electrical engineer to ensure that the installation is safe and compliant with all applicable codes and standards. Now, let's examine some of the potential hazards associated with using the wrong type of transformer or misapplying a transformer. Firstly, there is the risk of electrical shock. If the transformer is not properly grounded, or if there is a fault in the transformer's insulation, there is a risk of electrical shock to anyone who comes into contact with the transformer case or the connected equipment. Secondly, there is the risk of fire. If the transformer is overloaded, or if there is a fault in the transformer's windings, there is a risk of fire. The transformer's oil or other insulating materials can ignite, causing a fire that can spread to other parts of the building. Thirdly, there is the risk of equipment damage. If the transformer is not properly sized for the load, or if the voltage is not properly regulated, there is a risk of damage to the connected equipment. Overvoltage can damage sensitive electronic components, while undervoltage can cause motors to overheat and fail. Fourthly, there is the risk of power outages. If the transformer fails, it can cause a power outage that affects the entire building or area. This can disrupt business operations and cause inconvenience to residents. Fifthly, there is the risk of explosion. In extreme cases, a transformer failure can result in an explosion. This is more likely to occur with liquid-filled transformers, where the oil can vaporize and ignite, causing a violent explosion. To mitigate these risks, it is essential to follow all applicable codes and standards, use properly sized and rated equipment, and perform regular maintenance and inspections. Proper grounding is crucial for preventing electrical shock hazards. Overcurrent protection is essential for preventing fires and equipment damage. Regular inspections can help to identify potential problems before they lead to a failure. Now, let's consider some additional safety precautions that should be taken when working with transformers. Firstly, always energize the transformer before working on it. This means turning off the power at the source and verifying that the transformer is not energized with a voltage tester. Secondly, wear appropriate personal protective equipment, PPE, such as safety glasses, gloves, and insulated tools. This will help to protect you from electrical shock, burns, and other injuries. Thirdly, never work alone. Always have someone else present who can assist you in case of an emergency. Fourthly, be aware of your surroundings. Make sure that there are no obstacles or hazards in the work area. Fifthly, use proper lifting techniques. Transformers can be heavy, so use proper lifting techniques to avoid back injuries. Sixthly, dispose of used transformer oil properly. Transformer oil can be hazardous, so dispose of it according to local regulations. Seventhly, keep the transformer clean and dry. Dirt and moisture can degrade the transformer's insulation and lead to failures. Eighthly, inspect the transformer regularly for signs of damage such as cracks, leaks, or corrosion. Ninthly, listen for unusual noises such as humming, buzzing, or arcing. These noises can indicate a problem with the transformer. Tenthly, feel the transformer for excessive heat. Overheating can indicate an overload or a fault. By following these safety precautions, you can help to prevent accidents and injuries when working with transformers. In summary, selecting the right transformer, installing it correctly, and following proper safety precautions are essential for ensuring the safe and reliable operation of electrical systems. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns.